Welcome to today's paper reading. Today's paper is titled, MM1, Methods, Analysis and Insights from Multimodal LLM Pre-Training. This paper was published on the AR14 preprint by Brendan McKinzie and colleagues from Apple. In this work, the authors discuss the construction of performant multimodal large language models, MLMs. They specifically study the importance of various architecture components and data choices. Through comprehensive ablations, they identified several crucial design lessons. For instance, they found that a careful mix of image caption, interleaved image text, and text-only data is essential for achieving state-of-the-art few-shot results across multiple benchmarks. Additionally, they show that the image encoder, along with image resolution and token count, has substantial impact, whereas the vision language connector design is of comparatively less importance. By scaling up their approach, they built MM1, a family of multimodal models, including dense variants up to 30 B parameters and mixture of experts variants up to 64 B parameters, which are state-of-the-art in pre-training metrics and achieve competitive performance after supervised fine-tuning on various established multimodal benchmarks. The research community has made significant progress in language modeling and image understanding, largely due to the availability of large-scale image text data and computational resources. This has led to the development of highly performant large language models, LLMs, and vision foundation models. Multimodal large language models, MLMs, have emerged, combining these advances into a single model with superior capabilities. These models can perform in-context predictions, multi-image reasoning, and exhibit strong few-shot learning capabilities. In this paper, the authors contribute by performing ablations on model architecture decisions and pre-training data choices, and by scaling up models to achieve state-of-the-art performance. Figure 1 illustrates how MM1 leverages its large-scale multimodal pre-training to perform in-context predictions. This capability enables MM1 to a. Accurately count objects and adhere to custom formatting instructions, b. Identify and refer to specific parts of images while performing optical character recognition, OCR, c. Exhibit common sense understanding and word knowledge about everyday objects, and d. Execute basic mathematical functions. The images used in these demonstrations are sourced from the COCO 2014 validation set. Figure 2 demonstrates MM1's ability to follow instructions and reason across multiple images. This capability is illustrated through examples provided by Vila, 71, which correctly answers questions when prompted with a chain-of-thought approach. This figure highlights MM1's proficiency in handling complex visual tasks by integrating reasoning processes with visual data. The type of multimodal large language models, MLMs, discussed in this work are built upon a strong pre-trained autoregressive large language model, LLM, that processes both text and visual tokens, obtained through an image encoder. Our approach is based on a decoder-only architecture, similar to Cosmos 1. Recent research has increasingly focused on visual instruction tuning on top of the pre-trained LLM, with prominent examples including LLavier, MiniGPT-4, MPlugOwl, Otter, InstructBlip, and Honeybee. There is also a rich body of literature on constructing instruction tuning data and enabling MLMs for referring and grounding, as well as image generation and editing. The body of work that focuses on thorough ablations, particularly on the pre-training side, is relatively sparse. Vila studies various components of multimodal pre-training but lacks optimization details or detailed pre-training evaluations. EMU2 provides details regarding pre-training optimization parameters and base model results, but does not provide ablations justifying component decisions. IDFX provides details regarding large-scale multimodal pre-training but focuses primarily on replicating the closed-source Flamingo model. In contrast to these previous works, we aim to provide details regarding all components of our pre-training strategy, from hyperparameters to data to architecture, and provide extensive ablations on the precise impacts of decisions regarding visual encoders, vision language connectors, and pre-training data mixture. The construction of a performant multimodal large language model, MLLM, involves several key design decisions. Firstly, in terms of architecture, the choice of image encoder and how visual features are integrated with the language model are critical. This includes pre-training the image encoder and selecting an appropriate vision language connector. The resolution of the images also plays a significant role in model performance. Secondly, the data used for training is crucial. The balance between interleaved and captioned data, the inclusion of text-only data, and the use of synthetic data like VCAP all influence the model's capabilities. Finally, the training procedure itself, including hyperparameter tuning and stage-wise training, is essential for optimizing the model's performance. Performance is evaluated through zero-shot and few-shot tasks across various benchmarks. Figure 3 illustrates the model and data ablations conducted for MM1. On the left, it shows the model ablations focusing on the choice of visual encoder, how to feed rich visual data, and how to connect the visual representation to the LLM. The right side details the data ablations, examining the type of data and their mixture. Key points include the use of VITL/14 and VITH as visual encoders, the inclusion of captioned images, interleaved image text, and text-only data, and the exploration of average pooling, attention pooling, and C-abstractor as connector types. Table 1 presents the results of an ablation study on MM1 pre-training across various image encoders, using a 2.9B LLM. The study highlights the significant impact of image resolution, model size, and training data composition on downstream performance. Specifically, increasing image resolution from 224 to 336 results in a 3% boost across all metrics. Doubling the model size from VITL to VITH yields a modest performance increase of less than 1%. Additionally, incorporating VCAP 300M, a data set of synthetic captions, provides a more than 1% boost in few-shot scenarios. The study also notes that contrastive methods generally outperform reconstructive methods in terms of performance. Figure 4 presents the results of 0-shot, 4-shot, and 8-shot evaluations across various visual language connectors for two different image resolutions, 224px and 336px, and two image token sizes, 64 tokens and 144 tokens. The study aims to determine the impact of these factors on the performance of multimodal models. Key findings include that increasing the number of visual tokens or the image resolution generally improves performance, while the type of visual language connector has less conclusive effects. This suggests that the number of visual tokens and image resolution are more critical factors in enhancing model performance. Table 2 provides a comprehensive list of datasets used for pre-training multimodal large language models, MLMs. The datasets include 2 billion image text pairs sourced from CC3M, CC12M, KIP204M, COYO, and Web Image Text 1B. Additionally, 300 million synthetic image text pairs are provided by VCAP. The table also highlights 600 million interleaved image text documents from Obelix and Web Interleaved. These datasets are crucial for enhancing the capabilities of MLMs by providing diverse and extensive training data. Figure 5 presents an analysis of data ablations across various metrics including text core, 0-shot, 4-shot, and 8-shot. Subfigure A shows the impact of different mixing ratios between interleaved and captioned data on image data results. It highlights that increasing the amount of captioned data consistently improves zero-shot performance, while maintaining at least 50% interleaved data is essential for few-shot performance. Subfigure B demonstrates the effects of incorporating text-only data, revealing that combining text-only and captioned data boosts few-shot performance. Subfigure C explores the optimal mixing ratios between image data and text-only data to achieve strong multimodal performance. Finally, subfigure D examines the impact of including VCAP synthetic data, showing a non-trivial boost in few-shot performance. The final model configuration for MM1 multimodal pre-training is determined by the results of previous ablations. The image encoder is a VITH model with a resolution of 378 by 378, pre-trained using a clip objective on DFN5B. The vision language connector uses 144 tokens and employs the C-abstractor architecture, where the specific architecture is less critical. The data mix includes 45% interleaved image text documents, 45% image-text pair documents, and 10% text-only documents to maintain both zero and few-shot performance. Figure 6 illustrates the relationship between the size of a model and the optimal peak learning rate required to achieve close to optimal 8-shot performance. Each data point on the graph represents an experiment where the model size was varied, and the learning rate was adjusted to find the optimal setting for 8-shot performance. The graph suggests that as model size increases, the optimal learning rate decreases. This relationship is extrapolated using a linear regression model applied in log space, which helps in predicting the optimal learning rate for larger models based on the observed trends from smaller models. Table 3 presents the results of multimodal pre-training evaluations, highlighting the performance of MM1 models across various benchmarks. The table shows that MM1 significantly outperforms previous work in few-shot scenarios, particularly at the 30B model size, where it achieves superior results in captioning tasks and the VisWizQA benchmark. On VQA-V2, Text VQA, and OKVQA, MM1's 30B model is comparable to EMU2. The table also notes that MM1 performs well in zero-shot scenarios without instruction fine-tuning, demonstrating favorable results on text caps across all model sizes and being comparable to Flamingo 3B at smaller scales for most benchmarks. In this section, we discuss the supervised fine-tuning (SFT) experiments conducted on pre-trained models. The SFT data mixture includes approximately 1.45 million examples from various datasets, such as instruction response pairs generated by GPT-4 and GPT-4v. For high-resolution SFT, we employ positional embedding interpolation and subimage decomposition to support image resolutions up to 1792 by 1792. The SFT results demonstrate that our models outperform state-of-the-art models, particularly in benchmarks like VQA-V2 and Text VQA. Additionally, our mixture of experts, MO, models consistently show improved performance across benchmarks. The impact of image resolution in pre-training is also significant, with higher resolutions generally leading to better performance, and more pre-training data consistently improving model capabilities. Table 4 presents a comprehensive comparison of MM1 models against state-of-the-art, SOTA, models across various multimodal language model, LLM, benchmarks. The table highlights that MM1-3B chat and MM1-7B chat set new state-of-the-art performances for their respective model sizes, outperforming all listed models of the same size. Notably, MM1-3B chat and MM1-7B chat exhibit particularly strong performance on benchmarks such as VQA-V2, Text VQA, ScienceQA, MMU, and MathVista. Additionally, MM1-30B chat outperforms EMU2 chat 37B and CogVLM 30B on Text VQA, SEED, and MMU, demonstrating competitive performance across the board. Figure 7 illustrates the impact of image resolution and pre-training on the performance of SFT. Specifically, it shows a 15% relative increase in performance when the image resolution is increased to 1344 by 1344 pixels compared to a baseline of 336 pixels. However, a slight decrease in performance is observed at the highest resolution of 1792 by 1792, likely due to resizing artifacts affecting smaller evaluation images. Additionally, the figure examines the effect of pre-training steps on SFT performance. In this study, the authors explored methods to build highly performant multilingual large language models, MLMs. By systematically analyzing various modeling and data choices, they identified crucial lessons that led to a pre-trained model achieving state-of-the-art results in a variety of few-shot evaluations. Following supervised fine-tuning, SFT, this model family demonstrated competitive performance across a broad spectrum of benchmarks, while also enabling capabilities such as multi-image reasoning and few-shot prompting. The authors hope that these identified lessons will provide valuable guidance to the research community, facilitating the development of robust models that are not limited to any single specific model architecture or data strategy. Thank you for watching.